Greetings everyone. Welcome back into Calc 1 where we're going to finish up our unit on antiderivatives and integrals, and next unit we'll be moving into applications of those. To sort of finish up what we're talking about here with our main functions that we hit all of the time are the integrals that involve inverse trig. Now this doesn't mean I'm going to be integrating inverse trig or doing the antiderivatives of inverse trig functions. These are going to be the integrals that result in inverse trig answers. Those are the ones that typically happen. And these are very interesting integrals because of the way the inverse trig derivative rules have already shown us that we sort of leave the realm of trig a little bit and cross back over into the radical rational polynomial type of world. And so the antiderivatives, the integrals, will be crossing back in the other direction. We'll start with integrals that have those rational radical type of setups with a lot of squares being thrown all over the place, right? And then our solutions will have the inverse trig functions as the main structure of the answer. So all of these three rules are based off of the derivative rules that you've already experienced in the derivative unit a couple of units ago. They're just in reverse, right? So integral 1 over square root of a squared minus x squared dx is inverse sine of x over a. And of course, if you feel like throwing a negative in there, you can also do inverse cosine instead. Same thing with all of these, right? If you throw the negative in, you can do the inverse of the reciprocal. Typically, we just stick with these main three, though. So let's get some examples going on here. For our first example here, I'm going to show you how sometimes the integral can just be manipulated slightly and then just be something that falls right into the pattern and can be integrated immediately. In this one, I can already see that I can bring the 5 out of the integral. But also I'm noting that I can factor a 16 out of the binomial in a denominator. And if I factor it all the way out, I'll actually have to do the square root of the 16, which is a 4. So that's going to result in me having a 5 over 4 on the outside of the integral. And then I'll have just dt over, this will be the square root of 1 minus t squared. Now don't let this throw you off if you have the dt here at the top. It's really 1 times the differential, right? This is 1 times dt. So this is really the same thing as this. Look at it. 1 is a squared, so a must be 1. And x squared, I have t squared. So this one's ready to be integrated. I'm just going to get 5 over 4 arc sine of t over 1, right? Because that's over that, plus c. And that's it. So if you can do a slight number manipulation, no big deal. And then you can do your antiderivative. Some of these will require substitutions. And of course, recognizing the structure beforehand. This looks a lot like one of the integrals that I did in the last lecture that had to do with using logarithms and multiplying exponentials. The difference in this one is that I can see the two different exponentials and they've got two different powers. One is 1x, one is 2x. That's a big key. That's telling me that I have a couple of squares in the bottom, right? This is going to be a squared function, and 4 is also a squared value. So that sort of waves a big red flag for this kind of setup right here, the a squared plus x squared. And then seeing the e to a single x in the top seals the deal that that must be some sort of derivative of a substitution where the squared is not part of the substitution. The squared is part of the structure, which would scream this setup right here. Okay, so let's take a look. I'm going to rewrite this integral as, I'm going to pull the 7 out, and I'm going to have e to the x on the top, and it's going to be 2 squared plus e to the x squared, and my dx is right there. And remember, that's what it means when you have two things multiplied in an exponent, right? It's the two things, one power raised to another. Okay, this is ready for a U substitution. Look, right here, if I just let u equal e to the x, then du is also e to the x dx, because derivative of e to the x is itself. I have the u right here. I have the du right here. It's immediately ready for a direct substitution there. Okay, so I end up with 7 integral 1 over 2 squared plus u squared du, which is exactly what I've got up here. Okay, so what I have is 7 over 2, because it's over a, arctangent of u over 2 plus c. Okay, but now I'm going to come back from the substituted universe. U is equal to e to the x. So what I've actually got here is 7 over 2 arctangent of e to the x divided by 2 plus c. All right. If you see this kind of structure, I mean, it's kind of going to be blatantly obvious that you have the variable times the square root in the denominator. That one screams arcsecant, inverse secant integral. Okay? The difference with this one versus the other two is I don't have a way to just factor a number out that's the same like I did in this first one. And I don't have a complicated function like this one. It's just needing a little bit of number manipulation, but in a slightly different way than the first one. I'm going to have to play with the numbers a little bit. First thing though, I'm going to bring the negative 13 out. Right? Definitely I'm going to do that. That's going to leave me with a 1 in the dx here. I'll go ahead and separate the dx out. Okay, now the square root here, I'm going to write it as 3x squared, and then the minus 2 is right there. And the reason why I do that is because the structure of these trig functions, these inverse trig functions, they need to have one object, one variable, x squared. So if I can treat this, instead of having the 9 times the x squared, that doesn't look like I can accommodate because this doesn't have a number in front, right? Instead, I consolidate the 9x squared as 3x all squared. So 3x must be the thing taking the place of my x squared there. Well, these two things have to match, and all I've got on the outside over here is just an x. So that this and this match, that's what my pattern shows here, I am going to multiply a 3 here. That's actually a division because the 3 is in the bottom. So that means I'm also going to have to multiply a 3 up here. All right. Well, that means it's ready now. Look at it. I can just replace like this. I can say that u is equal to 3x, right? So du is equal to 3 dx. Actually, this will be convenient. Here's what I'll do. I won't multiply the 3 there. I'll multiply the 3 that I was fixing right here. I'll just take that same 3 and multiply it right here instead. So look, now I've got my 3 dx. Right? Okay. And then also, I'll have my 3x here and my 3x here. So I can directly substitute now. I'll have negative 13 integral 1 over u square root of u squared minus 2 du. I still don't have it totally like that pattern though, because the a squared needs to go there. how can I take the number 2 and write it as something squared? Well, instead of 2, I'll just write the square root of 2 squared right there, instead of just 2. Then I now can see that my a value of this one is going to have to be the square root of 2. So then I'll do the antiderivative here. That's going to be negative 13 over a, so it's over square root of 2, inverse secant of u is my variable right now, square root of 2, plus c. And then I'll hop back out for my antiderivative with x. So I'll have negative 13 over square root of 2, arc secant of 3x was my u, over square root of 2 plus c. All right? So that's the basics of using these inverse trig functions. Let's just get a couple of more examples before we wrap up. Let's sneak in 3 more examples using these kinds of antiderivatives just to get some other variety and practice in here, all right? So let's start off here. This doesn't look anything like a lot of those other integrals that we were doing, right? It doesn't have 2 terms in the bottom, and it doesn't just have the squared. It's a fraction over a quadratic. In this case, you need to try and think outside of the box a little bit. Go back to your algebra days and remember there are ways of rewriting quadratics such that they are a squared parentheses object plus some other number. And in this case, that would be extremely useful if I could rewrite this as some parentheses squared plus some number. Because if I could do that, then I could treat the denominator like x squared plus number squared, which would be right in the realm of my arctangent, as long as the thing inside of the parentheses wasn't overly complicated and in need of a huge, weird substitution. Well, quadratics are perfect for that, because if I complete the square, then what I get inside of these parentheses is just something linear, x to the 1. Easy substitution derivatives for those. All right, so that's what I'm going to do. I'm going to complete the square on this denominator so that I can get this structure that I'm gunning for, right? So, okay, I'm just going to go work on the side for a second to complete the square on this thing. So I've got my x squared minus 10x plus 31. And I want to complete the square on this. What that means is I'm going to take x squared minus 10x, and I'm going to separate that plus 31 out. I'm going to take half of the negative 10 as my parentheses, like this. Half of the negative 10 is 5. And if it's going to be squared, then that means I needed a plus 25 here. The way I make that work is I put a minus 25 right next to it. And then these 3 pieces right here factor into this piece. And then these 2 are just going to straight up add so that I have plus 6. Okay? If you're a little bit shaky on completing the square, I recommend running over to my college algebra series. I've got an entire video that talks about solving quadratics and completing the square and quadratic formula along with it. Okay? Definitely a good thing to practice, because this completing the square thing is not going away. It does keep coming up with many of the methods here in Calc 1, and also in the second semester course in Calculus 2. There will be a lot of completing the square necessary at different locations. So what that means is this expression is equal to that expression. if you were to multiply this out and add the 6, you would get this back. Okay, so basically I'm rewriting my integral here. Integral of -2 over x minus 5 quantity squared plus 6 dx. Now, of course, the -2 is just a number that I can bring out, okay? And the x minus 5 is something that I can substitute to make it a single object, to make it look like my inverse trig function. So that's what I'm going to do. I'm going to let u equal x minus 5. That would cause du to equal dx, because the derivative of x is 1. Okay, so I'm going to do that substitution here. And it's going to give me an integral that looks like this. -2 integral 1 over u squared plus 6 dx. Okay? Now remember, I need something squared here also. I need an a squared value. And since it's 6, what I'm going to do is I'm just going to square root and square that. So my a value is actually the square root of 6 squared. Okay, so that gives me -2 over square root of 6 times arctangent of u over square root of 6 plus c. And then my u value was x minus 5. So to finish up, I have -2 over square root of 6 arctangent of x minus 5 over the square root of 6 plus c. And then I've got a nice antiderivative to this normal looking rational function. Okay, next, another advanced looking structure, but take a step back. Remember, think outside of the box. If I see an arc sign in an integral, I can pretty much expect, well, wait a minute, we don't really talk about the antiderivatives of those. That's probably part of a substitution. So if I take this piece right here out, look at what I'm left with. Number over a square root with a difference of squares there. That looks just like the derivative of an arc sign, doesn't it? Well, that means if this were u, right, if I let this be u, then hopefully what's left over would be related to du. Let's find out. If I let u equal to inverse sine x over 2, then du would be the derivative of him, right? Derivative of inverse sine is 1 over square root of, in this case it would be 2 squared minus x squared. Okay? Dx. Well, great. That's exactly what we have. I have a dx over 4 minus x squared in a radical. The 3 is extra. So perfect. What did I end up with? I ended up with, after the substitution, the 3 is still there. U took the place of that. And both of these got replaced with du. Like so. Right? So then the antiderivative is 3 over 2 u squared plus c. And then to finish that up, what I have is 3 over 2 arc sine of x over 2, that whole quantity squared. I don't have a shorthand for that one unless I want to write it the other way of the inverse trig, right? I could write it like this. Those two are the same thing. And if I don't have to write it with the little inverse symbol, then it won't get mixed up with the squared, right? If I write it as arc sine instead of inverse sine, they're synonymous. And then I can actually use my shorthand with the squared there. But either one of those is completely fine. Okay. Last one over here. It's a definite integral, right? Don't let that throw you off, right? We'll use a substitution and everything will be just fine. But oh my goodness, that one looks completely bonkers, doesn't it? Except I'm seeing something in the bottom that has two structures. It has a simple one and a not so simple one, and they're added. And there's a squared in there, right? With two things being added in the bottom. This looks an awful lot like something with two squares being added together in the bottom. Well, I see the x that I can factor out there, and if I rewrote this squared a little bit more with the parentheses, maybe it would make sense. So let's try that. So if I factor out the x in the bottom like this, 1 over x times 1 over 1 plus ln x squared dx. So you see I factor the x out of the denominator, and then I rewrite the ln with the parentheses structure to sort of give myself that visual inspection of the structure. And I realize, oh, wait a minute, 1 over x is the derivative of ln x. And then I have 1 over 1 plus something squared. That's an arctangent integral. So I'm just going to do a substitution, right? Let's let u equal to ln x, the inside piece. Therefore, du would be equal to 1 over x dx, which I have already, right? All right, so then this is going to be equal to the integral of 1 over 1 plus u squared du, which is a perfect arctangent. But wait a minute, I've got to convert the numbers, right? U is equal to ln x. So this is going to be equal to the ln of 1, which is 0, and the ln of 3, which is irrational, so I'll just write ln of 3. Because u is equal to whatever the ln of the x's, and the x's were 1 and 3. Well, all right, so next step. The antiderivative here is just going to be arctangent, inverse tangent of u. And u varies from 0 to ln 3, right? All right. So then next, all I have to do is plug in top minus bottom. So that's going to be the arctangent of ln 3 minus arctangent of 0. Well, nicely enough, arctangent of 0 is 0. So that piece is gone. And I'm left with this as my final answer for the exact value. Let's see what we're talking about here. Make sure you're in radian mode, right? Because we're always going to do radians with these things. So I'm hitting radians. I'm going to hit inverse tangent ln 3. And I get 0.8324-ish. Nice. So I hope this has helped you succinctly finish up practicing all of your antiderivative rules and also incorporating all of the substitutions, because that is a major integral structure that you need to be able to perform. And stay tuned for the next unit, which is on some applications of integrals, including different kinds of areas that we can do, and even upgrading into volumes of symmetric solids.